Welcome to Generally AI Season 2, Episode 2. As a fun fact to get started with, I discovered last week that Edgar W. Dijkstra invented his shortest path algorithm in 20 minutes on a terrace of a cafe in the Netherlands. And he was wondering what the shortest path is from Rotterdam to Groningen. And apparently he didn't even use a pencil and paper when inventing it. And he says that helped him avoid all the avoidable complexities. And I think that taking 20 minutes to think about a solution seems acceptable for a lead code problem like this. What do you think?
I feel like most of my candidates are not in the same class as the esteemed professor, but yeah, why not?
I think so too. The other fun fact I have for you, by the way, is that when he started publishing his algorithms, the first 5 years, he didn't use a machine. So basically, he and the other researchers would just look at the algorithm for a super long time to convince them that it was correct and would work. So that's a good unit test, I guess.
It's good code review anyway. So there's a similar anecdote, but I think it was a different guy who said, I have not tested this code. I've merely proved it correct.
Well, that's the other thing, is that there wasn't a notion yet of proof of correctness for algorithms. And at some point, he had a call for algorithms for a conference. And so many people submitted algorithms he could find a counter case for that he just told these mathematicians or logicians or whatever it was at the time, before computer science was computer science. He basically told them, you have to submit your algorithm and a proof of correctness. And apparently, immediately someone submitted that, and then he knew it was correct.
Nice.
I will tell you one last other fun fact. The shortest sub-spanning tree algorithm was initially invented to save copper wire on a big electric panel because you want to ground all the points to the same place. So you want to find the shortest amount of copper, which helps with that.
That's amazing. It's funny how much all this harkens back to the hardware world.
Yeah, but then in that time, these algorithms make sense.
Yeah. So I don't have a fun fact so much as a fun anecdote. And this was a blog post from a very long time ago where a mathematician noticed that mathematicians who were specialists in algebra ate their corn on the cob one way, and the ones from analysis ate theirs in a different way.
Interesting.
With eating corn on the cob, you can basically go
left to right,
raster pattern.
Yeah.
And the other way is to go around the whole thing and then move and go around the whole thing. And so the algebraists eat in the raster pattern and the analysts eat in spirals.
Interesting.
Nobody's sure what that means or how general it is, but it seemed to hold true for most of the people this guy polled.
Nice. Interesting. I will also, by the way, send you the link to the interview in which Edgar Dijkstra said this. Welcome to Generally AI Season 2, Episode 2, where I, Roland Meertens, will be discussing our favorite algorithms with Anthony Alford.
Hey, Roland. Well, it's interesting. We started out with the fun facts about algorithms, and I've spent the last few weeks trying to think, what is my favorite algorithm?
What is your favorite algorithm?
Well, before I get to that, I started thinking, as I do, where do algorithms come from? The answer may surprise you. Do you have a guess where algorithms come from?
I don't know, but I have a pretty good sense of algorithm.
Nice. Well, algorithms come from Uzbekistan. Let me explain. In the land that is today known as Uzbekistan, there's a region called Khwarezm. And this was, a long time ago, the home of a man named Muhammad ibn Musa al-Khwarizmi. Actually, that's what al-Khwarizmi means. It's someone from Khwarezm.
No way.
Right? Surprise. By the way, as an aside, this is what we call a toponymic surname, a surname that comes from a place name. Fun fact. Anyway, today we usually just refer to this man as al-Khwarizmi. He was born approximately the year 780, and in about the year 820, he was appointed as an astronomer and the head of the House of Wisdom in the city of Baghdad. So there was a lot going on at the House of Wisdom back then. This was during a cultural golden age. The house was a library, an academy, a research center. Scholars were translating ancient Greek texts, as well as doing a lot of original work. And some of the work that Al-Khwarizmi did was he wrote a book. He wrote it in Arabic, of course, a book about how to do calculations using the Hindu numerals. So, as you no doubt know, ancient people like the Greeks and Romans didn't have the place value number system that we use today. Yeah. They used letters for numbers. For example, Roman numerals for 1, 10, 100, 1000, those are all different letters from the alphabet.
Yes.
Whereas we just use a number 1, the numeral 1, and we add zeros. They didn't have zeros.
Who did not have zeros? The Greeks and the Romans?
Anybody.
Nobody had zeros.
Somebody had to invent the zero.
Once someone did extremely poorly on a math test, they had to invent a new number to grade them.
You're cracking me up. That's like that Happy Gilmore sketch. Anyway, somewhere between the 1st and 4th centuries, our modern numeral system was invented in India, and it spread to the Islamic world and eventually to Al-Khwarizmi. And he wrote a very influential book on how to use these numerals and the positional system to do arithmetic. And even today, we still call these numerals Hindu Arabic.
Yeah.
Sadly, his original text is lost, but it was translated into Latin. And in the process, Al-Khwarizmi's name was Latinized, variously to Algorismi, Algorismus, Algorithmi. And the translation of his book was called Algoritmi de Numero Indorum, or in English, Al-Khwarizmi on the Hindu Art of Reckoning. So spoiler alert, our word algorithm comes from the name Al-Khwarizmi. So I'm sure many of you listeners knew that. I'm sure you knew that too, Roland. But
I did not know this. So I really enjoy this fun fact.
Right. So that's where the word comes from. Now, a brief digression. When we talk about an algorithm, what does that mean? And Wikipedia says it's a finite sequence of mathematically rigorous instructions typically used to solve a class of specific problems or perform a computation.
Seems fair, yeah.
Yeah. So the first algorithms that most of us learn as young students are those for doing basic arithmetic, addition and subtraction. And that's what Al-Khwarizmi's book was, a book of algorithms. Originally, his Latinized name, Algorismus, became synonymous with the number system. And the technique of doing arithmetic with this system was actually called algorithm.
Is it like there's algorithm and algebra, right? So that is not coming from the same thing?
You're getting ahead of me.
Okay, I'm speedrunning this podcast.
Foreshadowing. Yes, actually, we will talk about algebra. They're both Arabic words, right? The same word in alchemy and alcohol. A lot of words that start with al are actually Arabic in origin. Yeah.
Okay.
Anyway, as I said earlier, his work was translated into Latin. It was introduced to the West about the 12th century, but it didn't really take the Western world by storm at first. It was probably known only to a few intellectuals.
Yeah.
So what did help to popularize it was a 13th century book called Liber Abaci. It was written in the year 1202 by Leonardo of Pisa.
Oh.
There's another toponymic surname. He's better known to us today as Fibonacci.
Oh, interesting.
Actually, Fibonacci is short for Filius Bonacci, which means the son of Bonacci, and we would call that a patronymic surname. So
we just became a word fun facts podcast.
Well, I mean, I love etymology. What's good, he's got that alias, because when I think of Leonardo and Pisa, I think about Leonardo da Vinci dropping cannonballs off the Tower of Pisa.
Yeah, but so there were more intellectuals in Pisa.
Yeah, well, he was much later. And by the way, da Vinci is another toponymic surname. But I digress. Back to Fibonacci's book, Liber Abaci. The title is a little confusing, at least to those of us who don't speak Latin, and I'm one of those, because it sounds like it might be a book about how to use an abacus. In fact, it describes methods of doing calculation without an abacus, but with using that Hindu numeral system. So it's actually instructions on how to use Al-Khwarizmi's algorithms.
So at this point in time, did people already adapt the Arabic number system, or were people still using the Roman number system?
So this book was what started the adoption of those numerals in the West.
Yeah, because of the easy algorithms for addition and subtraction.
But it didn't take over completely. And according to Wikipedia, again, for centuries after this book, the people who followed it were called the algorithmists, but there was also people who were called abacists, who were the traditionalists. They had that abacus, you could take it from my cold, dead hands attitude.
If you are a listener who is still hoarding out, please contact us. We will want to interview you.
Yes. Well, again, a digression. For those of you who have read the book by Richard Feynman, surely you're joking, Mr. Feynman.
Yeah, great book.
Doesn't he have a scene where he's going head to head with an abacus guy doing calculations?
Yeah, indeed.
The abacus guy could beat him on some stuff, but then like Feynman was a Nobel Prize winning physicist. It would be hard to beat him in some math problems, I think.
Yeah, I think the thing is that there wasn't needed an abacus salesman, which at that time is a thing because there's no calculator yet. So you have abacus salesman, which I think is already first amazing thing. And then someone in a cafe starts giving them mathematics problems. And before calculators, people would be really good at simplifying the problems, right? Yeah. So he just knows how to simplify the things, and then it's quicker than the person who's just moving all these beats around.
I wonder if he got to use a slide rule or something like that.
No, so he was just doing it in his head.
He was just doing it in his head.
Yeah.
Amazing. So that's the power of the algorithm.
Yeah, indeed.
All right. Well, so back to Fibonacci. Of course, he's probably most famous for that sequence that's named after him, where the next number in the sequence is the sum of the previous two. So 1, 2, 3, 5, 8, 13.
Yes.
So if your story points are 13 or more, you probably need to break that story.
Yeah, this person did not invent the story points, but he did invent the numbering system.
So calculating the nth number in that sequence, that's often a favorite way for instructors in programming to demonstrate recursion, because you can write a very neat little recursive function that, given an input in, it will return the nth number in the sequence. And I think it's probably a pretty popular software interview question. Now, that's probably a controversial topic on Reddit or Hacker News or something like that. But I think there are some nice things about it. So, for example, the common recursive implementation gives you a platform to talk about complexity of that algorithm, right? By the way, do you know the complexity of the recursive Fibonacci calculation?
We talked about algorithms for this in the previous podcast.
Did we?
Yeah, in the previous season, because I think we also found that there's numerical ways to approach it because you have to calculate the previous number.
It's exponential. Actually, it turns out the complexity is the Fibonacci number.
Oh, okay.
So anyway, and then you could talk about, well, how do you speed it up? And the answer is you can use memoization.
Yeah.
Spoiler alert, I'm going to call this my favorite algorithm, right? So there's non-recursive implementations, such as iteratively calculating it. But my favorite way is to use the golden ratio.
Oh.
And in mathematics, the golden ratio, two quantities are in the golden ratio if their ratio to each other is the same as the ratio of their sum to the bigger of the two. So 3 to 5, it should be in approximately the same ratio as 5 is to 8.
Yeah.
And so forth. So that golden ratio is approximately 1.618. You can calculate the closed form of it. It's 1 plus the square root of 5 over 2.
Yeah.
And then the square root of 5 is 2.236 approximately.
Yeah.
So you can approximate the nth Fibonacci number by taking that golden ratio, 1.618, raising it to the nth power, and then dividing by the square root of 5.
And it gives you an approximation, right? It's not exact.
It's not exact. You just basically round, but the error is very small.
Oh, interesting. How big is the error then?
It's less than 0.01, I think, once you get past like the fourth or fifth Fibonacci number.
Fantastic.
So that's my favorite algorithm. But as they say on TV, wait, there's more. I want to make an AI connection. And you kind of spoiled this for me. No. So besides his work with the number system, Al-Khwarizmi wrote another book, The English title is The Compendious Book on Calculation by Completion and Balancing, which sounds like something that might be found in the Hogwarts library.
Yes.
But anyway, this introduced systematic methods for solving linear and quadratic equations. So the Arabic title of this book, which I am not going to try to read, but it contains the word algebra, which is the part about restoring broken parts. And that is where we get the word algebra.
So it was the same person. It was the person named Algorithmus.
Yep.
Who also gave us the word algebra.
Yes, that's correct.
Interesting.
So, yeah, and his approach involved standard operations. So you might say he had algorithms for doing algebra. We have him to thank for algorithms, for the decimal system, and algebra. And so the AI connection is, of course, linear algebra. Right?
Yeah.
That's the foundation of neural networks.
The people in the House of Knowledge must love the current AI hype.
Yes, they're well past the, the trough of despair. I forget.
Yeah, indeed.
So that is my favorite algorithm. I actually have two. I have the Fibonacci sequence and also algorithm himself.
Yeah. Your favorite algorithm is Mr. Algorithm himself.
That's right.
I love the approximate Fibonacci algorithm.
I forgot we had talked about that, but...
Well, we mentioned it, but we never really explained it. So I really like it. Hey folks, have you ever wondered how software leaders pushing the boundaries in today's environment are adopting emerging trends? At QCon San Francisco, November 18 to 22, you will step inside the minds of the engineers who will share how they implement innovations in real-world scenarios. Explore tracks like architectures you've always wondered about, engineering productivity, and, my favorite, generative AI in production and advancements. Here, you can learn from practicing senior software developers on how they are adopting emerging trends. Find out more about the conference at QConSF.com. We hope to see you there. All right. So from my side, I really like that you took an algorithm to approximate the Fibonacci sequence, because I want to talk with you about probabilistic counting.
That sounds like fun.
It is fun. Probabilistic counting sounds like something which shouldn't exist because either you count it or you don't, but sometimes you want to have a reasonable estimate is good enough, like in the case of a Fibonacci sequence. And the thing I want to do today is I want to talk about an algorithm, but I also want to talk about how I modified it a bit. So the thing is that whenever I visit a conference, I talk to a lot of people. But I always wonder how many unique people did I talk to? Because sometimes you talk to the same person again, and maybe you already forgot them. So I came up with an approach to this problem, but I first want to talk about the algorithm which inspired this. And that is that if you are a website like Reddit or YouTube, you want to know how many unique people visited your website or listened to your podcast. And it is possible that someone listens to the same podcast twice. Maybe people started listening to this and now they dropped out during the break and they come back later. And you don't want to count them all as unique listeners, right? You don't want to say that we have, I don't know how many thousand listeners, whereas actually it's half of them. So you don't want to double count.
Maybe you do and maybe you don't.
Yeah, depending on how good you want to feel, you do or you don't. And also in this case, for our podcast, I don't really care about the exact number. I do want to know a rough estimate.
Right.
And the naive way to solve this problem is that every time someone listens to our podcast, we add a name to a list, and then we turn that into a set, removing all the duplicates. Then we just count the cardinality of the set. So we count the number of people in the set, and that will take a lot of compute, and that will have a lot of memory. Hopefully we need a lot of memory to count all the listeners.
For this podcast, absolutely. We're going to need several terabytes.
If you have more than 5 people. So the algorithm which people have there is called HyperLogLog and does probabilistic counting. Do you know HyperLogLog?
I've heard of it. So obviously I'm interested in the etymology. Can you explain the name?
So I think at some point someone made an algorithm called HyperLog, and then people improved and called it HyperLogLog, and I think there's even HyperLogLog++.
Oh my goodness.
At some point I was on a holiday in Portugal and I started reading all these papers, but this is already 5 years ago, so I forgot the intricate details.
Interesting.
But yeah, so it's probabilistic counting. So it's not actually counting, but you're using probabilities to estimate the count of the size of a set. And in the case of our website, imagine we have a website. Actually, the Reddit blog is how I first found this algorithm, because they are using this to estimate things. And the approach is as follows. Imagine that each person who is browsing Reddit has a unique ID. And that's somehow encoded by their browser, IP, I don't know, hardware. So everybody has a unique thing to them. So we can track them on Reddit. So if they visit the same post twice, they have the same unique name. And for easiness sakes, let's just say it's their name, right? So like the computer's named Anthony or Roland. So what you do is you can take the hash of that number. So you take the ID someone has, you take a hash of that number. And I'm not going to explain what a hash function is, but this hash, when viewing it as a binary number, has an equal probability of a 1 or a 0 in each location.
Oh, interesting.
Hopefully. If you have a good hash function,
right,
it's equally likely that if you look at the binary representation, there's a 1 or a 0 in each spot.
Got it.
Now, the interesting thing is that you can treat this hash, this 0, 1, 0, 1, 1, 0, 1, you can treat this as a dice roll, or you can treat it as consecutive coin flips. So if you do this, you can start counting the number of leading zeros. And for example, if you have a number, there's a 1 in 2 chance that your hash starts with 1 leading zero. And a 1 in 4 chance you have 2 leading zeros.
Right.
And 1 in 8 that you have 3 leading zeros. And you can see where it's going. If you see that someone has 8 leading zeros, the chance was 1 in 256. And 16 leading zeros, you only have a chance of 1 in 65,536.
Buy a lottery ticket.
Yeah, but so the nice thing is that as a website, the only thing you have to keep count of is the maximum number of leading zeros which you saw someone have.
Oh.
So if you had a lot of people visit your website, you don't know exactly how much, but you do know that you saw someone with 8 leading zeros.
You've had 256 people.
The mathematical expectation is that 256 people listen to your podcast.
That's cool.
If you just saw all these numbers flip by, right? And you saw at some point someone with 16 leading zeros, you expect there to have been around 65,536 people.
Right.
Yeah, so the only memory you need is one number. Like you only need 4 bits or 8 bits or whatever, how many people you expect.
Well, heck, let's go 32.
Yeah, you only need 32 bits to count an estimate of the number of people.
So are you going to tell us about how much the error band is there?
Yeah, and this is also where algorithms like, I think this the idea of something like HyperLog. I'm not entirely sure which algorithm introduces what concept, but you could also, of course, take a look at what's the number of leading zeros for different hash functions, what's the number of leading zeros at different places in the same hash. So what you can start doing is you can start making buckets. So you take the first 4 zeros and then have different buckets, and then you count the rest of the leading zeros for the rest of the number. And that way you can already get way better approximations, and you can take the harmonic mean of these numbers to
not the golden mean.
It's not the golden ratio. No, it's a harmonic mean. I will also admit that I don't know exactly what all the possible mathematical means are. So you can use different tricks to get to better approximations of these numbers.
That's pretty cool. I really love that, just counting the number of zeros. Super simple. And it's probably not extremely accurate, but like you said, is it good enough? Might be.
for just giving someone a quick estimate of how well their post is doing, it's probably good enough. And as I said, the error band is lower as you add more of these buckets. Then you start having a larger memory footprint, but your memory footprint is still insanely small for counting millions of people.
Yeah, exactly. So it sounds like you need a couple of things. One, you need a way to uniquely identify each person, and then you need one or more hash functions that meet this criterion that they're balanced like that.
Well, yeah, so you need one. I think Bloom filters work on it's some kind of structure for your data. But it's again probabilistic, where you can check whether an element is in your Bloom filter by using multiple hash functions.
Gotcha.
In this case, you just assume that you have one, and that gives you a probabilistic 1 or 0 for all the numbers.
Okay. Nice.
So not all the hash functions work, right? But some do.
Right. Well, we probably won't, but we could do an entire episode on the different types of hash functions.
That sounds like something for the next season.
What's your favorite hash function?
I really don't know. I spent a lot of time trying to explain the concept of a hash function to non-technical people, and I have not found a good way to do it. So if you have one and find one, like if you find the way to explain a hash function to non-technical people, please let me know.
I don't think I've ever had the need. I guess you could maybe do it for a product manager. Right.
As you can see, I'm a lot of fun at parties, but I also like to go to parties and ask people what their favorite algorithm is.
What do you get for answers?
Well, I always tell them about HyperLogLog.
Oh, okay.
But someone last week told me they liked the stable matching algorithm.
Okay. Well.
Which is a way of making pairs of people using preferences where both people want to go for a different preference.
Okay.
Long story. Anyways, coming back to my original question.
Yes, please.
How many people did I talk to at a conference? What I figured is that instead of remembering every name, I can simply remember the alphabetically lowest name. And then afterwards, I can look at the probability someone has that name or alphabetically lower and see what the estimated people is which I needed to talk to find someone named like that. So if I go to a conference and I talk to one person, when you're sorting all the possible names and the number of people who are born in the UK, there's a 50% chance that their name is lower than the name Keith.
Really?
Yeah, but only 25% is alphabetically lower than Divian. So I downloaded the dataset of baby names from 1996 till 2021, which I will also put in the show notes. At the 12.5 percentile, so 1/8 chance is the name Babukar. And then if we halve that again, we get to the name Elvin. So I figured this is a great way of, you only have to remember one name, then you look it up in your dataset of baby names, and then you can have an estimate of how many people you talk to. And I think, you can improve it by remembering alphabetically the lowest name for each letter if you're talking to a lot of people. And then you take the harmonic mean, and then you have a better estimate for how many people you talk to.
So what was your number?
I never do this. I always think it would be fun to try this with a crowd, by just asking in the crowd, what is the alphabetically lowest name you all have? So maybe if we ever do QCon live.
Well, I was going to say at your next party, you should do that.
Yeah, so you can estimate the cardinality of your party.
So you got to have ground truth. I was going to say I would just do like they do voting in some countries where make everybody I talk to, I would dip their finger in paint and then I would know if I talk to them again.
I'm mostly wondering is that if I start estimating cardinality of my parties, I can soon count it on one hand. So I don't even need my abacus.
Put a turnstile at the door.
Yeah, indeed.
That's pretty fun. I love that algorithm.
Thanks. It's my favorite algorithm. Words of wisdom. Did you learn anything recently? Did you dive into something?
Just Al-Khwarizmi and the House of Wisdom. Definitely a lot of interesting scholarship there.
Yeah, are there other famous things which have come out of the House of Wisdom?
I think Al-Khwarizmi did some work on astronomy, so he did some catalogs of stars and things like that.
Yeah, interesting. Did he also ever treat him as a clock like we discussed in one episode last season?
That I do not know.
Because I have seen more people referencing to using Jupiter as a clock. So it's getting more and more settled that this in my brain that this used to be a normal way of counting time.
Interesting.
Yeah.
Around Jupiter time.
Well, I don't know to what extent people kept track of that. Methods of keeping and tracking time really intrigued me somehow. The one thing which I learned last week, a couple of days ago, at night, at some point, I couldn't sleep anymore because I had to answer the following question. You know that the eyesight of an eagle is way better than that of a human, right? Like 4 to 8 times better.
Right.
How do they measure this?
They have the eagle read off the eye chart. I don't know.
Yeah, it uses its wing to indicate it's pointing left, pointing up, pointing right.
You're going to tell me.
Well, yeah, indeed. So I spent a bit of time trying to figure this out when I should have gone to bed. So I was thinking, how do they do this? Can they mathematically calculate this? Is this something intrinsic to the eye where you can treat it as a lens and you can do something with that? Or do they do an eye test? But then how do they do this? I have gone quite far. So what I figured out they do is they have a long tunnel and they teach the ego that they put something on a specific screen. So if a screen has a specific pattern, it can fly through the tunnel and land on that screen. So the pattern could be, I don't know, let's just assume that the pattern would be a photo of a mouse. I don't know what the actual pattern is. Maybe they do something else. Let's say that the ego flies through a tunnel. There's 2 screens at the end. One screen shows a mouse. The other screen shows a fire truck. If it lands on top of the screen with the mouse, it gets a treat. It gets food. And what they do is that they have the eagle fly through the tunnel towards the screens. And then they show different sizes of this pattern on the screen. And then they look at when the eagle starts deviating towards the correct screen. And then they know that at that distance, they have perceived the pattern correctly.
Okay. Whereas a person has to get a lot closer before they get their treat.
Well, yeah, we can easily communicate with human and ask them to name letters.
I definitely want them to use grad students in this experiment and make them work for treats.
Yeah. So what I tried to do after I found this, I thought I really want to see how they conduct such an eye test for egos, if this is something which they do regularly. I could not find this on YouTube. So that's my other request for listeners. If you know someone who is conducting eye tests on egos, please reach out to us and send us a video. I'm very interested in this.
So we can estimate how many people know this by we figure out the name of the person who emails us.
Yeah, if you now listen to this podcast, and so sometimes I think, oh, I know more about this than the podcast maker. Should I email them? No, they probably get a lot of emails. Don't be like that. Please do send us an email. I really want to see this. And I will put a link to the webpage where I learned about this in the show notes.
I may have to go spend the rest of my evening looking that up.
Please tell me what you find. If you find the video, that's what I would love to see. If I can conduct an eye test on any kind of different animals, I would love to see that. Thank you very much for listening to this episode. And if you like this podcast, please tell your friends about it. Share it with the world. Thank you, Anthony, for joining again.
It was a lot of fun. I learned a lot.
Perfect. All right.
Cut.